study how to add binary numbers to n bit values. Technique is add individual bits, then propagate carries. For example, we have first value is 10101 and the second is 11001. We have to add these two strings of binary, and we have equivalent decimal numbers 21 and 25, that is 21 and 25. So first we will add binary numbers. First bit of the first string is 1 and the first bit of the second string from rightmost is again 1. So 1 plus 1 is 0, 1 plus 1 is 1 0. So we will take 0 as result, 1 as carry, and again 0 plus 0 plus 1, 0 plus 0 is always 0, and we will add carry to the next group, that is 1. So the 0 plus 0 plus 1 will be result as 1 and no carry. Then again 1 plus 1, that is third bit from the right, 1 plus 0 for both strings, 1 plus 0 is 1, and again fourth bit from right for both strings, 0 plus 1 is 1, and for last bit from right or first bit from left we have two values 1 and 1. 1 plus 1 is 1 0, 1 plus 1 is 1 0. There is one carry that will be added in the result, and the result is 1 0 1 1 1 0. So same equivalent number we will add 21 and 25, like 5 plus 1 is equal to 6, 2 plus 2 is 4. It is the most commonly used number system, decimal number system, that is used in all areas, and the binary number system is used by computer system. So the method of addition is same, but the rules for addition of bits are different as compared to decimal number system. Now we will study how to multiply. First we will take the example of decimal number system, how to multiply a decimal number system to a decimal number system. We will take two values. First is 35 and the second is 105. Here the cross sign represent, that is multiplication operation. Here we will multiply 35 by 5. The result is 175. First we will multiply 5 by 5. The result is 5 and the carry is 2. Then we will multiply 5 by 3. The carry is 2 and the result is 15. That makes 17. So the by 35 multiply by 5 is equal to 175. And in next row we will write the result from by multiplying 0 into 35, that is 0 0 0, because anything multiplied by 0 is 0. Again we will multiply 1 by 35, that is 35, and the result is 3675. No doubt it is very easy process, everyone knows how to multiply two decimal numbers, but same process will be applied to multiplication of binary numbers. There are rules for binary multiplication. We have 0 0, a is equal to 0, b is equal to 0, 0 into 0 is 0. So if a is equal to 0 and b is equal to 1, then again result is 0, because anything multiplied by 0 is 0, and a is equal to 1 and b is equal to 0, then again result is 0, because anything multiplied by 0 is 0, and the last is a is equal to 1, b is equal to 1. If both the values are 1, the result of the multiplication will be 1. Now we will study it with the help of example. Two n bit values with base 2 binary values. As we have discussed decimal multiplication, this is again the same process. And the first string is 1110, second is 1011. From the second string we will take first bit from rightmost and multiply it by the first string. The result is 1110, because anything multiplied by the 1 represent the same value, so it results 1100. Again we will multiply it by 1, that is 1110, again multiply by 0, so it will result in 0. Then last bit is 1 for second string, it will result in 1110, and we will add these values in the manner as is represented in screen, that is 0, and the result will be 0 1 0 1 1 0 0 1. The addition method is as binary addition we have studied, and we will get the multiplication of these two strings. Now we will study code, that is binary coded decimal, is also known as BCD. It would be easy for you if you can replace a decimal number with an individual binary code, such as if we have a value 0 0 0 1 1 0 0 1, then it will be represented as 1 9 in binary. Here the 8421 code is a type of BCD to do that, where 1 represents 2 raised to power 0, that is 2 raised to power 0 is always 1, anything raised to power 0 is always 1, and 2 represents 2 raised to power 1, that is 2, and the 4 represents 2 raised to power 3, 2 raised to power 2, that is 4, and the 8 represents 2 raised to power 3. Each raised to power n represent the position of the bit. So 8421 is the BCD code. BCD code provides an excellent interface to binary systems. It can be used by keypad inputs and digital readouts. Now we will take example how to convert an decimal number system to an BCD code. We have a decimal value 7093 having base 10, and we will convert it to BCD, binary coded decimal. We will take binary values for all digits of the given value. For 3 we have a binary value 0011. For 9 it is 1001. For 0 it is 0000. For 7 it is 0111. We are taking 4 bits to represent each digit, because for at least we need 4 bits for for representation of values up to 9. These are the representation of BCD values from 0 to 9. BCD 0 to 9 digits of decimal number system are represented as BCD numbers as follows. For 0 it is 000, and for 1 it is 001, and for 2 it is 0010. For 3 it is 0011. For 4 it is 0100. For 5 it is 0101. For 6 it is 0110, and for 7 it is 0110. For 8 it is 1000. For 9 it is 1001. So we are taking 4 bit values, because the largest number in the decimal number system, the largest value digit is 9, and we need at least 4 bits to represent this value. So we should have at least 4 bits to represent a BCD, a decimal number in a BCD number system. Now we will study how to perform BCD addition, that is binary coded decimal addition. BCD is a numerical code and can be used in arithmetic operations. BCD is a numeric code and can be used in arithmetic operations. Arithmetic means addition, subtraction. Here is how to add two BCD numbers. There is a procedure to apply addition on two numbers of multiple bits. And the first step is that add two BCD numbers using rules for basic binary addition. Then if a 4-bit sum is equal to or less than 9, if the resulting sum is equal to 9 or less than 9, it is a valid BCD number. It will be considered as valid BCD number, because we have range of valid BCD number is from 0 to 9. If a 4-bit sum is greater than 9, then it is an invalid BCD number. If a 4-bit sum is greater than 9, or if a carry out of 4-bit group is generated, it is an invalid result. In two conditions, if a result is less than 9 or a carry is generated from a 4-bit group, then the result is invalid. So to remove this problem, we will add 6 to a 4-bit sum in order to skip the 6 invalid states and return the code to 8421. That is, the code for 6 in binary is 0 1 1 0. So we will add 0 1 1 0 to the resulting sum, to a 4-bit sum, in order to skip the 6 the invalid states and return the code to 8421, that is BCD code. If a carry results when 6 is added, simply add the carry to the next 4-bit group. It means we will make another group of 4 bits. Now we will study the gray code. Gray code is a unweighted and is not an arithmetic code, because in this code every digit or every bit do not have a specified position and a specified value. There are no specific weights assigned to the bit positions. These positions of bits are changed periodically. That's why this gray code is not a weighted code, it is an unweighted code, because any bit position has not assigned a particular weight. The gray code exhibits only a single bit change from one code word to the next in sequence. There are comparisons of decimal number system and with binary and gray code. If we have 0 in decimal number system, we will have binary number system have 0 0 0 0, and in gray code we have 0 0 0. For 1 it is 0 0 1 in binary and 0 0 1 in gray code. For 0 and 1, two representations are same, binary and gray, but for decimal 2, binary and gray code representations are different. For binary it is 0 0 1 0, and for gray code it is 0 0 1 1, and for 3 it is 0 0 1 1, and for gray it is 0 0 1 1, and so on. For as we are studied that from 0 to 15 decimal values, binary and gray codes are represented in this table. Now we will study how to convert from a gray code, from binary code to gray code, and how from gray to binary. The gray code, binary to gray code conversion. Technique for this is, the most significant bit in the gray code is the same as corresponding most significant bit in the binary number. So we will take it as most significant bit of a gray binary code as same as in gray code. Going from left to right, add each adjacent pairs of the binary code bits to get the next gray code bit, and then discard carries. For example, we have 1 0 1 1 0, 1 MS, most significant bit MS, we take 1 as 1, and starting from left, 1 plus 0 results 1, discard carry, there is no carry. 0 plus 1 again results 1, then 1 plus 1 results 1 0, discard carry and take the result 0, then again 1 plus 0 is 1. That is the gray code for the given binary code is 1 1 1 0 and 1. Now we will study how to convert a gray to binary conversion. The MSB in the binary code is the same as the corresponding bit in the gray code, as we have studied in from binary to gray. Add each binary code bit generated to the gray code bit in the next adjacent point, discard carries. For example, 1 will be represented most significant bit as 1, and we will add the result most significant bit of the binary number system to the adjacent bit of the gray code. That will be 1 plus 1 represent 1 0, we will take it as 0 and discard carry, that is 1. Again we have result 0 and the next bit is 0 of gray code. 0 plus 1, we will take it as diagonal addition. 0 plus 0 is 0, 0 plus 1 is 1, and 1 plus 1 is again 1 0, we will take it as 0, 0 as in result, and 1 will be discarded. So our result from gray to binary is 1 0 0 1 0. So all this is all about data representation in computer architecture.